Hi everybody, my name is Sara Barsotti and I'm the coordinator for volcanic hazards at the Icelandic Meteorological Office. Within this video I'm going to talk about numerical models for the simulation of the transport of tephra in the atmosphere and its deposition. So numerical models are powerful tools actually to investigate the dynamics of several natural phenomena, not only volcanic eruption. However, numerical tools, they are a kind of simplified version of the reality. And in this sense, we need to make sure which is their usage, which are the assumptions behind the numerical models, which are their limitations, and of course even which are their constraints before using them. So within this video we are going to look into what exists. So the literature is quite wide and extended on this topic. Today I'm going to discuss a few key things that might help in describing, deciding and understanding the usage of such tools. There is a variety of numerical models that are used for the simulation of the dispersal of tephra in the atmosphere. They might resolve the equations in 1D, 2D, 3D, and 4D when it is accounting for even the temporal factors. And in the recent years, the volcanological community, it has been really encouraging and fostering the use of such a tool by collecting and making available a list of codes that could be used by the community. So in here, under the page of the Tephra Hazard Modeling Commission, there are several of these collections. It is under software, where it is possible actually to look into what is currently existing. So there is a kind of compilation of codes that are actually available. Some of them are just list of tools that people can just scroll through and select and choose which is the best software to use. Some others actually provides more information about metadata, references, and some of them is also possible to be run online. So the data flow when using numerical models is a kind of well-established procedure. As you can see here, there is a set of input parameters that needs to be given in input to the dispersal model. They comprise, for example, what we call the eruption source parameters. For example, information regarding the plume height, the mass eruption rate, but also information about the total grain size distribution, so which is the type of particles that are emitted within the eruption, and possibly even more detailed and harder parameters to estimate, like the vertical velocity. A numerical model, a dispersal numerical model, of course, needs meteorological data that either could be 3D or vertical profiles, that could be forecasting, or could be reanalysis data. And then often numerical models for dispersal, they also need information regarding the land usage and the topography. The type of output that can be produced by different dispersal models, it depends actually on the processes and how the numerical models are coded. But most of the time then we might think about having concentration in the atmosphere at the ground as a function of time, the total accumulation at the ground, but also information about the cloud height, the cloud thickness, as well as the arrival time. Again, all these parameters and how these outputs are calculated really depends on which type of software you are using. Of course, this process can become even more complex when this numerical code is part of a bigger algorithm. Here we are seeing indeed the addition of near real-time information coming from satellite. This is what we call a data assimilation process. This often is the case when these dispersal codes are part of operational response, where we can count on getting information about the eruption itself. So again, the eruption source parameters plus observation from satellite. These two things integrated together might allow to get an updated and more reliable forecast. The model results, they depend or are more sensitive to some key parameters. Some studies actually reveal that the results of dispersal simulation, they are indeed very sensitive to, for example, the total emitted mass. Here is an example where actually we can see the affected area for different thresholds and how it is indeed increasing by the increasing mass given an input to the model. However, it is also known that there are other parameters, like, for example, the settling velocity, so actually the velocity by which the particles are falling towards the ground, that has a major impact on the results. And here again is another example where we can see how using a variety of settling velocities in input to the model is giving as an output different extension of the impact on the ground. In fact, particles ejected into the atmosphere, they might have a wide range in shape and sphericity. This is an example, as you can see, where indeed mainly particles smaller than 2 millimeters, what we call ash, they can really show a wide range in these parameters. And that's mainly because their size and shape, it is mainly affected by the magma properties and the fragmentation dynamics. This is an example of ashes as it is seen from the lab. And it is pretty clear how irregular they are, how it is indeed very hard to make the assumption that could be a sphere. By using numerical models, then, it is possible really to evaluate which is the sensitivity of the model results to such properties. Here we are seeing 3 graphs showing which is the persistence of different particles characterized by different sizes into the atmosphere. So we can see the duration by which these particles persist into the atmosphere. And we can clearly see that starting from particles of a size above 100 micron, it is clear that either we are considering these particles to be spherical or to have a shape, then the duration of their persistence in the atmosphere, it becomes longer. This has a direct impact eventually on the forecast that we can do in order to evaluate and calculate which could be the impact on a wider scale. So this is another example where we can see different numerical simulations where a variety of input data for the total grain size distribution has been used. On one case, particles are spherical, or they've been using a variety different densities. And we can see how the contours of the concentration for the different particles that are becoming, they are actually getting longer or farther from the source, that in this case actually is the volcano Eyjafjallajökull in Iceland. Of course, the validity and reliability of the model results, they become even more important when decisions are taken based on the forecasting, for example. This is a case when there are evacuations to be called because of expected heavy tephra fallout, or because of the need of rerouting airplanes because of presence of volcanic ash in the atmosphere. So what we're seeing here is indeed a scheme that shows somehow the potential usage of a dispersal code throughout the life of a volcano. So we might think that when a volcano is in its quiet time, so nothing is really happening, we might still be using numerical dispersal model to evaluate which could be the impact on the long term. So what we call the long-term hazard assessment. And in this case, of course, we would be using information like what we know happened before at the volcano, which is the history, the historical activity at this volcano, and then designing scenarios based on that. Most of the time then we would be getting what we called probabilistic hazard results that could be used for land use planning. When a volcano should start to show some unrest, then we might start to think about updating such scenarios and in a way start to use or provide to the dispersal model information more accurate or more related to the event ongoing. And in this sense, we might start to use forecasting data in order to start to provide an anticipation of what might be happening if an eruption will start. And the last step, of course, is in case of an eruption when the volcano is indeed already emitting ash in the atmosphere. So then there will be all new bunches of information as we already see what we call the eruption source parameters would be likely and possibly estimated observation from satellite. So our numerical models will be potentially initialized with known parameters at the best, as we can indeed evaluate. Numerical weather prediction will be used in input to the dispersal model. And of course, what we will be getting will be forecasting result that will be used for alerting the general public, the civil aviation authorities, and the civil protection itself. In addition to that, it is a recent, quite well-established procedure to start to produce the probabilistic forecast. So running the code in order to perturbating either the eruption source parameters or perturbating the meteorology itself in order to be capable also to communicate, which is the uncertainty associated to the forecast. For a reliable and accurate prediction, then we need high quality and high frequency observation of the eruption, or again, those parameters that we call the eruption source parameters. For the long-term hazard assessment, indeed, what we need are reliable and good reconstruction of what the volcano produced in the past, in its historical activity. So there are a few initiatives that have been ongoing in the past years that are aimed in order to make accessible and available information like this. So there are databases that people can actually exploit to know more about volcanoes. One example is here. This is the database that has been produced within the IVESPA, the Independent Volcanic Eruption Source Parameters Archive, that is accessible through the Tephra Hazard Modeling Commission website, and there is a collection of information for a variety of volcanoes around the world. At European level, then, the newest European Catalogue of Volcanoes also provides information about which are the most likely scenarios that we expected eruptions at different volcanoes in Europe. So it is possible indeed to investigate this by choosing to look at this table that is very crowded. This is the aviation table. So for each volcano that is available through the catalog, it is possible to identify or find which are the reasonable worst vertical plume height, for example, that, as we heard, is one of the key input parameters that we need to know about the eruption source parameters, and which are the most likely duration. So there are a collection of information that indeed all those users that are interested in running this dispersal model might be interested to get access in order to design and simulate scenarios that can be considered reliable. Running a dispersal model by using even the best information in input, it is not actually guaranteeing the model is performing well. It is a fundamental step in the entire process of using and running softwares for the dispersal of Tephra that includes the validation of the model itself. This means somehow to be capable to quantify and assess how accurate the prediction is, how capable is the codel indeed to reconstruct what is actually happening. If it is possible in a way to have a good constraint, for example, on observation like the plume height, because we can see it or assess it through web cameras, or mass eruption rate based on inversion of models, then there is a key information like the total grain size distribution that still is bringing a huge uncertainty within the running a dispersal model. So here is an example about a recent study that has been actually investigating a reconstruction technique from the deposit. So in a way, how it is possible, starting from the information that we are collecting on the ground, to quantify the condition in input to the vent. Such studies are helping in order to be capable to answer questions like where I should put my collectors for sampling ashes, or how many points I should be using in order to reconstruct a proper and accurate total grain size distribution, eventually to be used in input to a dispersal model. Numerical models for the dispersal of Tephra in the atmosphere are operationally running at the Icelandic Meteorological Office. Here is an example of the webpage where the general public can have access to the latest simulations and just investigating which could be the impact or the distribution of Tephra and ash in the atmosphere. Specifically here, we are running the name code, which is also running at the UK Met Office at the London VAC. This is an example for today. So this is actually an hypothetical eruption. Grímsvötn volcano is not erupting today, but still we are each day trying to get ready. So we are always running scenarios, so eruptions for this volcano, and that's because this might be the next volcano erupting in Iceland. And here we are seeing the temporal evolution of the volcanic ash cloud in the atmosphere, as it is given with colors from the cyan up to the red. So we can see how it evolves as a function of time, how it extends and runs away from the emitting volcano. And at the same time, we also see in gray colors, which is the the accumulation of tephra on the ground. So this is showing how bigger and bigger is becoming the deposit or the amount of ash that eventually will be accumulated on the ground. Today we are having southwesterly wind, so in case of an eruption in Grímsvötn, the eastern part of the country would be most likely affected by tephra and ash. To summarize, as Box said in 1976, all models are wrong, but some are useful. In this sense, it is important when approaching numerical models to always keep in mind before interpreting the results, which are the usage, which is the application that we are doing of such a model. We always have to consider the importance and the relevance of using the best information we can collect regarding the eruption source parameters, or in general the scenario that we are or that we want simulating. And eventually, if we cannot really get access to high quality information, then we need to consider to communicate the uncertainty associated to the model results. There is, of course, an extended literature about numerical models, but for those that want to learn more about what has been just said within this video, here is a list of publications that are accessible for everybody.